Hi everyone, welcome to week 12 CEE222 recitation. So let's start it with this first problem, 8.5.2. So this problem tells us we have a 13.1 feet wide rectangle channel convey 72.2 cubic feet per second of flow. So B is equal to 13.1 feet and convey the flow equal to 72.7 CFS. And if we draw a diagram for that, we will have something like this. Okay, so this is the flow and this is the weir. Okay, and the question wants us to determine the depth of the water at the upstream area. And also determine the velocity. We call this depth of water h, and velocity v over the weir here. Okay, we want to know the v here. So to do that, we first need to know the water depth at here. I mean on top of this weir, and we know that for the flow transit from a subcritical to downstream, these depths will equal to the critical depth because the flow have a free flow over this weir. So that's why we have this y equal to yc. So we can simply apply the equation to calculate this critical flow for this rectangle channel. So the formula you can find in the textbook, equation 6.14, which I write out the formula equation for you. Look like this. Okay, so we just plug in the number which the flow rate is equal to 72.7 squared divided by g in the English unit, which is 32.2, times b, the width of the channel, which is 13.1 to the power of 2, then 103. Okay, so after the calculation, we will get the answer that the critical depth is equal to 0.985 feet. So now we already know the value for this yc is 0.85. Okay, so we can easily calculate the velocity at this point. Okay, at this cross section. So the velocity will equal to flow rate divided by the area, right? And the flow rate we already know that, which is 72.7. Area, because this is a rectangle channel, so the area is the water depth, which is yc, which is 0.985, times b, the width, which is 13.1 feet. So we can get that the velocity is equal to 5.63 feet per second. Okay, so to calculate the depth of water that will produce upstream of 3.28 feet height weir, we will apply the energy balance equation. In here, H will equal to the specific energy at this point, this cross section, plus the height of weir, which is this height of the weir. This is x. Okay, and to find out the reference for this equation, which is really just the energy equation, you can see the equation 8.7 in the textbook if you want to look why we have this equation. So we can further expand this. The specific energy is equal to 3/2 times the critical depth plus the height of weir, which is 3.28 in our question. And we plug in the critical depth that we just solved for YC. This YC is equal to 0.985. So we can solve this H, that is 4.76 feet. Okay, so this is a fairly straightforward question. You just need to apply two different questions, one for the critical depth, one for the energy, and you can solve these two variables for the velocity and the depth of the water. And one important assumption for this answer, this depth of water to be correct, is because we assume there's no head loss in this problem. So we can use this cross section, which is at the normal depth section, to calculate this depth of the water H. If we have the head loss, then you need to minus head loss at this. You need to further add the head loss to calculate the H, which we will see in next problem. Okay, now let's check the next problem, 8.5.6. So here we have a weir located in the channel that has the height equal to 1.4 meter and the width equal to 5 meter. And we have the water flow over this weir, that the depth above this weir, which is HS, that's equal to the energy grid line 2.6 minus the height of the weir, which is 1.4, that is 1.2 meter. Okay, 1.2 meter. Okay, so what else we know? Oh, carrying the flow of 10 cubic meter per second. So we know the Q is equal to 10 cubic meter per second. Okay, that's the all information that we know. And we want to determine the amount of the energy lost, HL, for this problem. And we want to determine the actual coefficient of the discharge, which that we want to solve the CD plum that is not equal to the theoretical number 1.7. Okay, so let's start to solve this. First, for frictionless weir, we can use the equation 8.8c in the textbook, which is written as Q equal to capital Q divided by B equal to 1.7 H is 3/2. Okay, but now we want to solve the actual coefficient CD plum, which is not equal to 1.7. But we will use this relationship to solve the CD plum. So we can further write it out that Q is equal to CD plum, H is to the power of 3/2. And because we know that the Q equal to the capital Q divided by B, which is 10 divided by 5. Because B is equal to 5 and Q is equal to 10, okay? So this is equal to 2. And we know H is equal to 1.2 as we calculated in this diagram here. So the entire things can be written into 2 equal to CD plum times 1.2 to the power of 3/2. Then we can solve that CD plum is equal to 1.52. Okay, let me erase this. So this already answered the first question. Why is that? What is the actual coefficient of the discharge in this weir? Then we can move on to solve the second thing, which is the energy lost in this problem. So according to the previous problem, we have the energy equation look like this, which you can find it at the equation 8.7 in the textbook, and we will use the similar concept here. So let's say the energy at the upstream area is equal to 3/2 times the critical flow plus the weir, and this is the energy at this cross section. But now, because we have the energy loss here, so we need to further add the energy lost because of this weir. So here you have the E up, and here you have the E plus the energy lost. Okay, so you can think that this is E. EW. Okay, then we can plug in the number, because we already know that the energy grid line at the upstream area is equal to 2.6. So this E up is equal to 2.6 meter. And we know the critical flow YC I read here is equal to Q squared divided by G to the power of 1/3. And we know Q is equal to 2. So let's just plug in the number. G is 9.81. So we know the critical depth is equal to 0.742 meter. Then we can plug the number back to this equation, this times 0.742 plus the height of the weir, which is x, this is x, so plus 1.4 plus the energy loss that we want to calculate. So using this equation, we can calculate the energy loss equal to 0.087 meter. Okay, so compared to the previous question, here we cannot ignore the energy loss because the problem want to ask what is the energy loss because of this weir. So the equation is slightly different from the previous one, which now we need to add this energy loss and compare the energy grid line at the upstream and at the weir. Okay. Okay, now let's look at the problem 8.6.3. In this problem, we want to evaluate a spillway, whether that can pass a design flood flow of 935 cubic feet per second. And after the evaluation, we will need to check, okay, if it cannot pass this design flood flow, what can we improve this design to accommodate this designed flood flow? Okay, so in the first step, we need to evaluate whether this design can pass our flood flow, which that's Q is equal to 335 CFS. Okay, so the equation for the flow rate for the spillway, you can find that the equation 8.9 in the textbook. And here I can write it down for you. That's the flow rate Q equal to, I will write this QF for the design flood flow, okay? And this Q is the flow rate of our designed spillway. The Q will equal to C times L times HS to the power of 3/2. And this C is the spillway coefficient. And the problem only tells us we can first assume that this C is equal to 3.5. And L is the width of the spillway, which is 30 feet in our case. And the HAs in this problem is 4.2 feet. So we just need to times 4.2 to the power of 3/2. So we can get the Q of the design spillway is 940 cubic feet per second. So this number is smaller than QF, the design flood flow, that is equal to the 900 feet. So the conclusion of this evaluation is that the design Q cannot be made under this condition. Okay, so the next step is how can we improve our design to accommodate this QF? So from this equation here, we can either improve the coefficient C, or we can increase the width of this spillway to increase Q. So in the case 1, let's try to design the spillway wider so we can accommodate the larger flow rate. So we want to test if we can increase the width. So now we want to design a width that can accommodate the flood flow, which is equal to 935, and the other is just remain the same, but now we want to calculate this L plumb. So by this equation, we can calculate that the width will have to be 31 feet. And in the second, and for the alternative, we can try to improve the spillway quality to enhance this spillway coefficient. Similarly, we apply the same equation, but now we calculate its C plumb and remain the order setting to be the same. Then we can get that the C plumb is equal to 3. Okay. 3.62. Okay, so from here, we solve this problem. We first use this equation to examine whether the designed flow is larger than the designed flood flow. And the results tell us, okay, the design Q cannot be met. Then we discuss two different cases that we can improve the design to accommodate this flood flow, which is either to increase the width of the spillway or to increase the spillway coefficient. Okay, now let's look at the last problem, which is more open and conceptual questions. So as the water moves through the hydrological cycle, water quality changes are common due to the natural phenomena or anthropogenic pollutions, and we want to see how the different process in this hydrological cycle can affect the water quality or the pollution issue. So I think I will just go over potential impact in different stage among this hydrological cycle. So let's start with the cloud. Okay, so condensation. So the cloud reaches the water droplets that they usually form around or condense around the dust or ocean salt particle or the particle from the coal-fired power plant. Okay, so basically for the condensation process, they need some particle to that the water vapor condense to the water droplet. And in the precipitation, the droplet will pick up the air pollution and bring them to the ground. Then those droplets will further become the runoff or intercepted by the tree leaves, and they will wash down the pollution that's on the surface of the leaves or wash out the pollution particles at the surface of the ground. And then in the evaporation process, only water will be evaporated. That means all the particle, all the salt, and other pollution particles will be left behind. So if that happened in a pond or a lake, then the concentration will just become higher as more water be evaporate. Okay. And in the infiltration process, the water will dissolve the salt or the nutrient inside the soil and further bring to the groundwater aquifer. So those particles will be bring down. Okay. I mean, will be dissolved first, then bring down to other area. And then we might have a plant that have a really deep roots that will uptake the water, while those water are polluted or contain lots of mineral or nutrient that will be absorbed by the tree through this transpiration. So that's, and those nutrients and minerals would then just accumulate inside those plants. And for the aquifer, it can either dissolve the nutrient inside the soil or transport the water with dissolved nutrient to other places. Okay, so that's basically about it. We already talked about the runoff. We already talked about the lake, because the lake will also have the evaporation that will increase the pollution concentration inside this lake. We talk about the tree might uptake the water from the soil, which those water contain the dissolved minerals and nutrients. We talk about the transpiration that brings the energy for trees to absorb the water from the ground. Okay, so I think these give you an overall view of how they affect the water quality in this different hydrological process.